The systems behind our universe are quantum mechanical. They shift and change with the problems they're tasked to solve, exploring a vast array of options all at once.
So this part is describing how quantum superposition allows these qubits or quantum bits to evaluate multiple possibilities simultaneously. And for classical algorithms, they explore one solution path at a time, and these quantum algorithms are able to explore all possible paths in parallel. And this ability is really what underpins the exponential speedup that we're seeing in quantum algorithms, like Shor's algorithm for factoring large integers. We have classical computers, which use fixed logic gates to process data, so transistors, and quantum computers leverage dynamic states of qubits. So because of superposition and entanglement, qubits adapt as the problem evolves, and this adaptability allows for optimization and parallelism that are orders of magnitude beyond what classical systems can achieve. For example, quantum computers can tackle combinatorial or optimization problems, like routing logistics or molecular modeling, much more efficiently than traditional methods. And this superposition is the cornerstone of quantum computing, which allows qubits, or quantum bits, to exist in multiple states simultaneously, unlike binary bits, which are limited to 0 or 1.
And like nature, quantum computing is responsive to the environments it works within, leading us to new breakthroughs for tomorrow's most challenging problems.
So these challenging problems that it's referring to are industries that might be revolutionized as a result of quantum computing. So things like pharmaceuticals, logistics, finance, cryptography has many use cases. For example, in drug discovery, quantum simulations of molecular interactions could potentially identify treatments that classical computers cannot model due to complexity constraints. And there's other potential optimizations in fields like logistics and even financial portfolio management.
Introducing our latest quantum computing chip, developed to learn and evolve like the natural world around us.
So this statement is really about the design philosophy behind Google's new chip. Classical chips are really static in function, but quantum chips are much more flexible. And so when it talks about evolution here, it's referring to the chip's ability to be tuned, reconfigured, and calibrated more dynamically, similar to how machine learning models improve over time. And this flexibility is very important for overcoming the high sensitivity of qubits to noise as well as interference.
Willow, from Google Quantum AI.
Hi, I'm Julian Kelly, Director of Hardware at Google Quantum AI. And today, on behalf of our amazing team, I'm proud to announce Willow.
Okay, so some context on Julian Kelly. He's the Director of Hardware. And so he's overseeing the design, the fabrication, and the improvement of Google's superconducting quantum chips, not just limited to Willow. And there's existing competition between Google and other companies like IBM and Rigetti. And of course, there's also Intel and D-Wave.
Willow is Google's newest and most powerful superconducting quantum computing chip, and the next step in our path towards building large-scale quantum computers and exploring their applications. I've been fascinated with quantum computing since I first experimented with qubits in 2008. And since coming to Google in 2015, it has been a dream to make our mission a reality, building quantum computers for otherwise unsolvable problems. We launched our first chip, Foxtail, in 2017, followed by Bristlecone in 2018 and Sycamore in 2019, which powered our milestone 1.
So if I go back to the timeline here, we see that Google has a pretty steady, methodical approach to quantum development, and each chip is actually representing a pretty significant milestone. So Foxtail in 2017 was the first superconducting qubit chip, and it was really Google's entry into the field. Bristlecone in 2018 featured 72 qubits, which improved the qubit count, and it also served as a testbed for error correction techniques, which we'll get to later. And Sycamore in 2019 demonstrated quantum supremacy by solving a computational problem exponentially faster than the best classical supercomputers could. So we don't want to overhype Willow, because in 2019 we've already proven that quantum computers are exponentially faster than classical supercomputers. We should note, however, that Willow does represent a significant leap forward in Google's quantum hardware roadmap. These superconducting qubits are operating at temperatures near absolute zero and use Josephson junctions to maintain quantum coherence. And quantum coherence is a fundamental property of quantum mechanics that describes the ability of a quantum system to maintain phase relationships and exist in multiple states simultaneously. It's very similar to parts of a wave being synchronized. The issue is that it's a very delicate state that's difficult to maintain for long periods of time, and interactions with the environment called decoherence cause phase shifts and uncertainty in the quantum states, which leads to the coherence fading. And quantum coherence is super core to quantum computing, But the main issue that researchers are trying to fix is how to minimize decoherence. And soon enough, Julie and Kelly is going to touch on error correction, which is one way to mitigate decoherence. There's also quantum sensor isolation, which can also help. And compared to Sycamore in 2019, Willow is introducing technological advancements that directly address the issues, like error rates, coherence times, and connectivity between qubits. And I do want to mention that coherence time is the amount of time a qubit can maintain its quantum state and be manipulated in calculations. It measures how well isolated qubits are and how long a given quantum state can maintain its phase relationship. And coherence time is an important parameter for evaluating the quality of qubits and the feasibility of quantum algorithms. So longer coherence times allows for more complex computations and reduces the need for error correction. So I mentioned maintaining phase relationships. So let me explain what phase relationships are, as well as why it's important. So maintaining phase relationships, or quantum coherence, is important because quantum states rely on superposition and interference to perform computations. And the relative phases between qubit states enable constructive and destructive interference, which is essential for quantum algorithms like Shor's and Grover's. And losing phase coherence due to decoherence disrupts this interference and collapses the quantum state into a classical one, which causes errors in the computation. And that's why we need error correction.
In Sycamore in 2019, which powered our milestone 1, the first quantum computer to surpass the best classical supercomputer on a computational task, random circuit sampling. Over the years with Sycamore, we have been able to squeeze a remarkable amount of performance from our hardware, including achieving a scalable logical qubit in our milestone 2. But we've ultimately been limited by quantum coherence times, the length of time qubits maintain their intended state. With Willow, we've made a huge step forward. We've increased quantum coherence times by a factor of 5, going from 20 microseconds in Sycamore to 100 microseconds in Willow.
Okay, so I mentioned what coherence time is. It's a very critical metric in quantum computing, and it indicates how long a qubit can maintain its quantum state before decoherence or loss of information occurs. And so we have this 5-fold increase from 20 to 100 microseconds from Sycamore to Willow. And this is going to allow Willow to run deeper circuits and enable more complex computations, because longer coherence means fewer errors, which is vital for achieving more scalable and fault-tolerant quantum computing.
Such this all without sacrificing any of the features that made our systems so successful. This advancement was enabled by our new dedicated superconducting quantum chip fabrication facility in Santa Barbara, one of only a few in the world.
So what this means is that Google has its in-house fabrication facility, which means faster iteration on quantum chip designs. And it also means supply chain independence and also the ability to develop custom hardware. Other industry players like IBM and Intel also have dedicated facilities. And this just means more control over fabrication, which helps avoid bottlenecks.
And we're seeing exciting developments coming from Willow, which has already surpassed Sycamore's breakthrough demonstrations. Our logical qubits now operate below the critical quantum error correction threshold.
So error correction is one of the biggest challenges. And these physical qubits are error prone. So logical qubits are created by combining multiple physical qubits to detect and correct errors. And operating below this error correction threshold means Google's error rates are low enough to make logical qubits viable.
A long sought-after goal for the quantum computing field since the theory was discovered in the 90s. And we've achieved it for the first time with Willow. Errors are exponentially suppressed in our logical qubits, as error rates are halved each time we add physical qubits and scale from distance 3 to 5 to 7 surface codes. Additionally, our logical qubit lifetimes are now much longer than all of the lifetimes of the physical qubits that compose them. This means that even as we make our quantum chips larger and more complex by adding more qubits, we can use quantum error correction to actually improve their accuracy. We've pitted Willow against one of the world's most powerful supercomputers with the random circuit sampling benchmark. The results are pretty surprising. By our best estimates, a calculation that takes Willow under 5 minutes would take the fastest supercomputer 10 to the 25 years. That's a 1.
Okay, so this is a very clear example of the quantum advantage, where we have quantum systems significantly outperforming classical supercomputers. And you can see for random circuit sampling, it's infeasible for classical machines, but because of the exponential speedup of quantum computing, it's done very efficiently in Willow. And so I imagine one of the most significant societal and technological implications of quantum computing is its potential to break widely used cryptographic protocols. For example, classic encryption schemes such as RSA and ECC, or elliptic curve cryptography, rely on the computational difficulty of problems like prime factorization and discrete logarithms. And currently, these problems are infeasible for classical computers to solve in a reasonable time frame. However, quantum algorithms like Shor's algorithm can factor large integers exponentially faster than classical methods. And this is going to pose a direct threat to RSA encryption, which is foundational to secure communications on the internet. For example, HTTPS, VPNs, encrypted emails, etc. So once quantum computers reach a sufficient qubit count and error correction capability, they will be able to decrypt current encrypted messages retroactively if those messages have been recorded. We have password-based authentication systems that rely on hashing functions that are now going to be vulnerable to Grover's algorithm. And what Grover's algorithm does is that it searches an unstructured list, like a password hash table, in quadratic time. And this means a 128-bit security level would be effectively reduced to 64 bits in quantum terms. And this will necessitate much longer passwords or the use of post-quantum cryptography. There's also secure banking protocols like TLS and SSL, which depend on public key cryptography. And so without post-quantum cryptography, financial transactions and payment systems could also be at risk. And this is also going to have some extended impact on blockchain and cryptocurrencies. So Bitcoin and other cryptocurrencies rely on ECC for wallet address generation. And a quantum computer could theoretically derive private keys from public keys. So a lot of these existing blockchain systems could be facing a security risk. So what we need is some kind of mitigation in this post-quantum cryptography realm. And we can call this post-quantum cryptography PQC. So there are already some existing efforts underway to develop cryptographic protocols that are resistant to quantum attacks. And these protocols, like lattice-based cryptography, are being standardized by organizations like NIST, or the National Institute of Standards and Technology. Perhaps a more short-term mitigation is key length adjustments, so increasing the key sizes for symmetric encryption algorithms like AES is one way to prepare for quantum threats, but it's definitely not a long-term mitigation. So while Grover's algorithm reduces key space search efficiency, doubling key lengths should be able to counteract this effect to some extent. The TLDR here is that as Google's quantum hardware progresses, we also have to invest more efforts in quantum-safe cryptography. And so my prediction is that the field of quantum cybersecurity is going to evolve rapidly, and more organizations are going to preemptively adopt PQC schemes. This is going to mean that governments, banks, and major corporations are going to plan for a post-quantum cryptographic migration in order to safeguard all of their critical infrastructure.
With 25 zeros following it, or a timescale way longer than the age of the universe. This result highlights the exponentially growing gap between classical and quantum computation for certain applications. Let's talk about the hardware approach we've pioneered at Google Quantum AI that makes these things possible. Our tunable qubits and couplers enable super fast gates and operations to achieve low error rates, reconfigurability to optimize hardware in situ and run multiple applications.
So these qubit couplers are enabling multi-qubit operations, for example, controlled NOT or CNOT gates. And by making these couplers tunable, Google is able to optimize the interaction strength between qubits and reduce error rates and boost computational fidelity.
And high connectivity to efficiently express algorithms. We leverage this tunability to enable reproducible high performance across the device. Let me explain. A challenge in superconducting qubits is that not all of them are created equal. Some are outliers with uncharacteristically high errors. But here's where our tunable qubits really shine. We're able to fix these outlier qubits by reconfiguring them to perform in line with the rest of the device. And we can go one step further by having our researchers use tunability to continuously develop new calibration strategies that push errors down across all qubits with software.
So even with advanced fabrication, physical qubits have variability in their performance, and identifying and mitigating errors from quote-unquote bad qubits is essential. And so dynamic tuning and error mapping ensure that these outlier bad qubits don't degrade the overall system performance. And so Google's ability to recalibrate these qubits post-manufacturing gives them a very significant edge.
Let's quantify this and nerd out for a minute on quantum computer tech specs. We have number of qubits. Connectivity is the average number of interactions each qubit can perform with its neighbors.
So it's important to contrast the fact that Willow has 105 qubits, and the previous generation Sycamore from 2019 had 53 qubits. But what's actually important is whether or not these qubits stay coherent or not. So yes, speed matters, but what's more important is actual coherence. Let's say instead of 105 qubits, we had 1,000,000 qubits. This doesn't actually matter if they can't stay entangled or coherent. But you really have to think of quantum computing like a graph. So each of the qubits is a node in the graph. But the issue is that a lot of these qubits are restricted by nearest neighbors. So you can't actually do full entanglement, which is a major limitation. And let me explain why that is. If a qubit does not have full entanglement and it can only interact with the neighbors around it, in this case the average connectivity is 3.47, it means that we have restricted quantum operations. A lot of these quantum algorithms rely on very complex interactions and relationships between qubits across the entire system, and when entanglement is limited to nearest neighbors, it's difficult or even impossible to implement these algorithms effectively. Think of it like solving a complex puzzle, but you can only move pieces that are next to each other. Your operations become very limited. Full entanglement also allows a much richer set of quantum states and operations, which directly translates to a broader range of problems that the quantum computer can tackle. So as quantum computers grow larger and you add more qubits, in this case we have 105, but imagine 1,000,000, the ability to entangle any qubit with any other becomes much, much more important. The TLDR is that nearest neighbor interactions create bottlenecks and also limit the scalability of the system. So for me, what I'm paying attention to is this average connectivity number. This number here is going to bottleneck Google's Willow chip. So fully entangleable can do nearest neighbors, but nearest neighbors cannot do fully entangleable. And this matters for gate operations. If you want to dig deeper into why that is, you can look up the no cloning algorithm and deep dive into that. There's also this concept of ion traps that enable full entanglement because of the Coulomb interaction at any distance. So what this means for Google is that superconducting can always add more raw qubits, but they are still low fidelity, and compounding errors will always end up with a meaningless answer. So you can have very fast superconducting, but it can be completely wrong. So my opinion here is that the challenge is not to scale up the number of qubits, it's to improve the quality. And we all know that superconductors are massive, and they have giant dilution freezers and compounding errors with increased physical size, and we need special power and custom-made physical locations to house them. And given that they also require linear processing and not all qubits are able to talk to each other, there's no physical way around this without error correction. But we should seriously consider ion traps, because they fit into current standard racks. They don't have to run near absolute zero. They run at normal room temperature and they're less prone to error. And they do have very incredible coherence times by comparison. And they can be interconnected, so you can create a single 256 AQ machine by linking 4 64 AQ machines. And this ability alone makes ion traps far more scalable and superconducting. But it still is a dream in the future.
We quantify error probabilities for running simultaneous operations. Single qubit gates, 2 qubit gates, and measurement. Coherence time measures how long each qubit can retain its information. Measurement rate is how many computations we can run per second. And application performance is a full system benchmark. Willow hits a sweet spot across the full list. It has a large number of qubits with high connectivity and can run diverse applications. We measure low mean error rates across all operations with multiple native 2 qubit gates. We have greatly increased T1 times. We have very high measurement rates, and Willow is below the error correction threshold and performs random circuit sampling far beyond what is possible with classical computers. Looking to the future with Willow, we continue our journey towards building large-scale and useful error-corrected quantum computers that will push the boundaries of science and the exploration of nature. With future commercially useful applications in areas like pharmaceuticals, batteries, and fusion power, we are excited to solve the otherwise unsolvable problems of tomorrow.
So one question you might be asking is, how do we verify that the results produced by this quantum computer are correct? And this kind of goes back to the P equals NP equation. A simple example has to do with prime factors. For example, finding prime factors x and y of a number n. For very large numbers, it's difficult to find x and y, but it's easy to verify by just multiplying x and y. So just because a problem is computationally difficult does not mean that it's computationally difficult to verify. Think of it like finding a needle in the haystack. It's tough to find the needle, but when you do find it, it's pretty easy to verify that it's in fact a needle. I also want to leave you with a pretty interesting analogy that I saw. You can think of a quantum computer as a plane and a classical or normal computer as a car. A plane arrives at some destinations very fast, much faster than a car, but sometimes for most normal applications, a car will be more suitable. So a plane unlocks international and global trade and unlocks new markets, but planes will never fully replace cars. For most applications, you won't even need a plane. So what quantum computers allow is for new massive tasks to be computed very efficiently, but they won't replace classical computers. But we will be using them for bigger tasks that cars cannot achieve. I also want to mention that some of the claims that I made in this video are slightly far-fetched. We're still very far from realistically breaking RSA with quantum computers. And this is because algorithms like Shor's does not scale very well. And in this video, they solved RCS, or random circuit sampling, but RCS has no actual real-world use case, other than a potential one in classical position verification, or CPV, but CPV itself is kind of fantasy land. So it's important to distinguish things that actually have impact on our lives, and arbitrary math problems that are intentionally computationally difficult, just for the sake of testing the computer hardware speeds. And you also may be wondering, are bitcoins no longer safe? Well, to provide a little bit of context on that, there are only a finite number of Bitcoin, and that number is 21 million, of which 19.5 million have already been mined. It will certainly accelerate the mining of the remaining 1.5 million, but considering all of the existing mined Bitcoins lost to date, I don't think it will have a very long-lasting impact. But you also have to consider the fact that the algorithm for mining just gets exponentially more complex. And this is tangentially related, but some people are speculating that all of our existing security algorithms are already compromised. But we still need a very large number of qubits to actually store data. So you can think of a common hashing algorithm like SHA-256, which would require millions of physical qubits to crack in a semi-reasonable amount of time. And these millions of physical qubits actually maps to about 3,000 logical qubits. So it means that we still have a long way to go, but even having a single qubit is pretty extraordinary compared to today's classical supercomputers. I also want to point out that sometimes these headlines are quite misleading, and a lot of the times it's full of sensationalism. So when Google Quantum AI is claiming that Willow solved a problem in seconds that would take a classical computer millennia, it's actually partially lying by omission, because it's leaving out the fact that the problem being solved by A, Willow, isn't a problem that's intended to be solved by B. So quantum computers are inherently designed to solve this class of problems, while classical computers are not intended to do so. So if you look at the big picture view, these current quantum computers are not really even computers at all, because they can't run software or applications. They can only really do a couple of very basic tasks. But yeah, that was a very long video, but hopefully you learned something new. Please leave a like and comment any outstanding questions down below. Also, feel free to subscribe to my channel for more updates like this. Thank you very much for watching, and as always, happy coding.